Hello everyone. Today I am going to explain about the fabrication of nMOS transistor, that is nMOS enhancement transistor. Okay, so here we have different steps to fabricate this nMOS transistor. Okay, so we have seen already that in the IC fabrication, so different steps we have seen, that is material preparation, crystal growth, wafer preparation, and after that we have wafer fabrication. So after that metallization and interconnections. Like that we have seen many steps in our IC fabrication. Similarly, here we have some fabrication steps for nMOS, and with some extra added steps we have some rules for CMOS also. Now today I am going with the nMOS fabrication process. Okay, so out of that, the first point or first step is we have to consider a wafer that is cut from silicon crystal. Okay, so in the wafer fabrication or wafer preparation, so after the crystal growth we will cut the silicon crystal into slices or wafers. Okay, so I will consider here in the first step that is the pure silicon wafer that is cutted from the silicon crystal. Okay, so that wafer I will consider here. After that, suppose here we have doing with nMOS fabrication. So nMOS fabrication means, so which material we have to consider as a substrate? So we have to consider p-type material as a substrate, lightly doped p-type material as a substrate. Therefore, how you can form a p substrate? So here after preparing the wafer, or after taking the wafer that consists of pure silicon. Okay, so into that pure silicon wafer, if you send the dopants, that is here we require the p-type semiconductor, p-type substrate, so we will send the trivalent atoms. Our trivalent atoms are the dopants or the impurities on the pure silicon wafer. Okay, so that there will be a formation of p substrate. Okay, what are the trivalent here? Boron, aluminum and gallium. Okay, so these gases will sent on the surface of the wafer, so that the pure silicon will become the p substrate. Okay, that is extrinsic semiconductor material it will becomes, that is of p-type semiconductor. Okay, so that's what the first step in the nMOS fabrication. So in the nMOS fabrication we are going to use the p substrate. That's why we will consider a wafer and we will process these trivalent atoms, boron, aluminum, gallium and indium. So any one of that will pass, and so that it will become the p substrate. This is what the first step. So here consider a thin wafer cut from a single crystal of high impurity. Okay, so this is nothing but after wafer preparation or crystal growth we will prepare the wafer, and that wafer we will consider that is a pure silicon with the 75 to 150 millimeter diameter. So what is the wafer diameter here? So it is of 75 to 150 millimeter. If you remember the steps of IC fabrication, it is very easy for us to learn this nMOS fabrication. So after taking the wafer with the diameter is 75 to 150 mm and 0.4 millimeter thickness. Okay, so this is the wafer we consider, into which impurities we have to send, that is p-type impurities are boron, aluminum and gallium, that is trivalent atoms we have to send, so that there will be a formation of p substrate. Then what is the doping concentration we have to use to convert the pure silicon into the p substrate is nothing but the doping concentration here 10 power 15 atoms per centimeter cube to 10 power 16 atoms per centimeter cube we have to consider the doping concentration. So because of sending of these impurities, onto the silicon wafer, pure silicon wafer with their doping concentrations or impurity concentrations are this, so that there will be a formation of P substrate. Okay, so this is the first step what we have while fabricating the nMOS transistor. Okay, so here after that what we have to do? So in the wafer preparation I have explained that what is the oxidation. Okay, so here now on the surface of the wafer we will place SiO2 layer. Okay, thick SiO2 layer of 1 micrometer. Okay, thickness of 1 micrometer thickness. So that's what here we have. How you can form SiO2 layer on the wafer means by oxidation we will form an SiO2 layer with 1 micrometer thickness on the surface of the wafer. So that is the second point we have here. So a layer of silicon dioxide SiO2 typically of 1 micrometer thickness is grown all over the surface of the wafer to protect the surface. To protect this surface of the wafer, we will place SiO2 layer of thickness 1 micrometer. Okay, so this green color representation I have done here on this diagram is nothing but SiO2 layer of thickness 1 micrometer. Okay, so this is the second step. How we can do is means we will do that one by oxidation process. Okay, so that is about the step 2. A layer of silicon dioxide typically of 1 micrometer thickness is grown all over the surface of the wafer to produce the surface, to protect the surface. Okay, so this is about the second step what we have in the fabrication of nMOS transistor. Okay, so the same steps will be applicable for the PMOS transistor fabrication with some changes. Okay, we will discuss that one later. First we will go with the steps of fabrication of nMOS transistor. This is the second step what we have. So after that, the nMOS transistor consists of or nMOS or PMOS consists of a source, drain and gate, and at the same time the channel space. Okay, between source and drain we have the channel. Okay, so in enhancement transistor we don't form any channel, but in depletion transistor we have to form the channel. We will discuss after that, after formation of this nMOS enhancement transistor fabrication. Okay, so now what I am doing in the third step is I am forming a layer of photoresist. A layer of photoresist on the SiO2 layer. Okay, so now that is the third step what we have. The surface is now covered with a photoresist material. Okay, so what is photoresist? Okay, so photoresist is nothing but if you send a light or if you expose to a light, that is UV light, ultraviolet light, so it has polymerized, or it will be softened, or it will be dissolved in the solvent. Okay, depending on this property, that is these photoresistors has divided into two types. Okay, so what is that photoresist means here? Positive photoresist, and second one is negative photoresist. So how many types of photoresist here we have? Positive photoresist and negative photoresist. Positive photoresist and negative photoresist. So how you can classify this one? Positive resist and negative resist means how they will behave, how the photoresist will behave if you expose that one to the UV light. Depending on that, we have divided this photoresist into positive photoresist and at the same time negative photoresist. Then what is the positive photoresist means? Whenever a UV light or the photoresist is exposed to the UV light, if it is dissolves or soluble in the developer or the solvent, then that is called as what? The positive photoresist. Okay, so it will easily dissolve or soluble in the developer, that is photoresist developer or the solvent. Okay, so then that type of photoresist is called as what? Positive photoresist. But the second type is what? The negative photoresist. Whenever a photoresist is exposed to the UV light, then it will be polymerized or hardened. Okay, hardened or polymerized. Then and at the same time, these materials or these photoresist materials, after the exposure to the UV light, they cannot solve in the developer or the solvent, photoresist solvent. Okay, one will be easily solvable in photoresist developer, that is positive resist, and another one is negative resist, that cannot be solvable after applying the UV light to that. So there will be a polymerized material will obtain, or it will be hardened. It cannot be dissolved in our solvent that is prepared to remove that. Okay, so this is about the two types of photoresist we have, that is positive photoresist and at the same time negative photoresist. Okay, out of that, both can be used in our semiconductor industry. There is no problem here. Okay, so here I am using here negative resist. Okay, I am going to use here to explain this. I am going to use negative resist, and at the same time the diagrams also drawn according to that. Okay, so these are the types of photoresist. Okay, now in the third step, what I am doing, after formation of the SiO2 layer on the wafer, now I am going to place our photoresist on the SiO2 layer. That is the third step. The surface is now covered with a photoresist material. Okay, so this is the SiO2, already I have indicated here. On that SiO2, what I am placing here is nothing but the negative photoresist. Okay, or the photoresist I am placing. Okay, the surface is now covered with a photoresist. So this blue color darkened place I will consider as a photoresist in our representation. Okay, so this one is what? Photoresist, and this one is what? SiO2 layer already we have formed, and this one is the P substrate that is obtained from the first step, and this is the SiO2 layer obtained from the second step, and the third step is we have to place the SiO2 layer is surface is covered with the photoresist. So after that, what we have to do? Okay, so I already told that an nMOS transistor that will be consist of nMOS enhancement transistor that will consist of the source, drain and gate. Okay, so this one is the source, suppose this one is drain and gate. So this is nothing but the nMOS enhancement transistor. It is a P substrate, and here we have N plus. One second. So here we have N plus and N plus. So this is the we have to fabricate the nMOS transistor that consists of like this. This is the P substrate, source and drain. Okay. Now what we will do after third step is we will define the regions where we have to form the source and drain and the gate. Okay, including the channel space. Okay, so now what I am doing here after this photoresist, okay, so I have to define the regions where we are going to accommodate the source, drain, gate and the channel. Okay, for that purpose I am using here photolithography. Then what is the photolithography means? Already we have discussed in IC fabrication. So we will prepare a mask. According to that, we will place that mask on the surface of the wafer or the photoresist, and we will pass the UV light. Okay. So here, that is the fourth step. We have the photoresist is exposed to the ultraviolet or UV light through a mask. The mask will be prepared in photolithography. Okay, so photoresist mask will be prepared in photolithography of IC fabrication. Similarly, here also we will prepare a mask. Okay, and we will place that mask on the photoresist layer so that we will pass that UV light. Okay, so that is the point. Here we have the photoresist is exposed to the ultraviolet light through a mask where we are going to define our source, drain and gate regions, including with the transistor channel. So that's why I am using this glass mask. The glass mask or reticle will be prepared at the time of photolithography in the computer, and at the same time that will be placed on this photoresist. Okay, so if you observe here, this UV light is falls on this photoresist layer. Okay, so this is the mask I have to use. That means step 4 is nothing but the photoresist is exposed to a ultraviolet light through a mask which defines those regions into which diffusion takes place, and that diffusion is nothing but source and drain formation, and at the same time the transistor channel. So that's why I am going to use above this photoresist layer, I am going to place a mask. Okay, so that mask is of a glass. Okay, a glass, and here if you observe this black color, it cannot allow the UV light, and here we have the transparent glass will be there. Okay, so at that point the light will be falls on the photoresist, and at this point the light cannot be falls on the photoresist. Okay, so therefore here we have, I am placing a mask on the photoresist and I am sending or I am exposing that photoresist to the UV light. So what happened here? So when I expose that photoresist, this is the photoresist, if it is exposed with the UV light by using the mask, okay, so here the UV light will passes here, here and here. The UV light will passes through this glass, and it is the photoresist is exposed to that UV light, and here that UV light cannot passes onto the photoresist because it is not a transparent glass, so it cannot be flows from that, it cannot be obtained from here to here. So this area cannot be exposed to the UV light. Okay, and whatever the area or whatever the photoresist that is exposed to the light will be what? Will be polymerized. Okay, so what happened this one? Here the photoresist will be polymerized. So this one is polymerized. Wherever the UV light is falls on the photoresist, so that area or that region will be polymerized. Polymerized means it will be hardened. Okay, it will be hardened. So here if you observe this one, this UV light is passing at this region, in this region, and at the same time in this region. Okay, then the material, photoresist material up to this point it will be polymerized or hardened, and at the same time from this point to this point also it will be polymerized. Okay, and wherever that light cannot falls on the photoresist, there is no change in that one. The material will be as it is, and that photoresist material will be removed by, or we can soluble in a solvent or the developer, photoresist developer, so that we can easily remove that. Okay, so that is the point we have here. There is no change. Okay, so now this is the fourth step what we have. We are applying the mask and we are passing the UV light. Wherever the UV light pass, that will be hardened and the remaining will be as it is. Okay. Now what is the next step we have? Okay. So in this next step we have to remove the photoresist, that is polymerized photoresist, and at the same time we have to remove our non-polymerized photoresist and the SiO2 under it. Okay. So what is the next step or fifth step here? We have to remove the polymerized photoresist and at the same time the non-polymerized photoresist and SiO2 under that non-polymerized photoresist by using different solvent, and at the same time this SiO2 will be removed by hydrofluoric acid. Okay. So what is that? So hydrofluoric acid. Fluoric acid. Okay, this removal of this material, unwanted material here, is called as what? Etching process. We have already, that is wet etching and dry etching, right? We have seen that. The same process here we are going to use to remove this polymerized photoresist and at the same time unpolymerized photoresist and the SiO2 under that unpolymerized photoresist. Okay, understood this fifth step. So this is the step 5. Remove the polymerized photoresist and non-polymerized photoresist together with underlying SiO2. So if you observe this one, this material will become hard and this material will become hard up to this point. Okay, up to this point this will become hardened, and the remaining material is nothing but here. This is the photoresist, that is unpolymerized photoresist. Unpolymerized photoresist, under it what we have? SiO2. Okay. So now what we have to do in step 5 is nothing but we have to remove the polymerized photoresist. At the same time we have to remove unpolymerized photoresist and SiO2 under it. So that means what? We have to remove this one and this one at a time, and at the same time this polymerized photoresist. So that's what here we have. So in the next step we have removed this photoresist and the SiO2 under it. Photoresist, SiO2 under it, and this one is what? The polymerized photoresist. Okay, so this one is what? The polymerized photoresist. Unpolymerized or non-polymerized photoresist will be removed, and SiO2 is also removed by etching process. By etching process we are going to use here that hydrofluoric acid. Okay, that is nothing but the acid that is used to remove this non-polymerized photoresist and SiO2 under it. Okay, so this is after removal of, this diagram will indicate after the removal of non-polymerized photoresist and the SiO2 under it. Okay, I am keeping that one as it is, here the polymerized photoresist, and in the next diagram I can show that this polymerized photoresist. Okay. After removal of polymerized photoresist, we will grown a thin oxide layer of SiO2 over the entire surface of the thickness with 0.1 micrometer. Okay. So here already we have some part, this is thick SiO2, and here also we have the thick SiO2. Next what we will do is we will place thin SiO2 throughout the surface of the wafer. Okay. So including this above this thick SiO2, here I am representing that thin SiO2 as like this, and its height is of 0.1 micrometer thickness. Okay. So next this is actual SiO2 or thick SiO2 what we have done in the second step, that is what 1 micrometer. So after this what we have to do is we have to place our source and drain, and at the same time we have to form the gate. Okay, for that purpose again we are going to use the mask. Okay, whenever you are going to use the mask means you have to use the photoresist here. Okay, after using the photoresist we have to place the mask on that. Okay, so that the required region will be formed. Okay, So that's why here in the seventh step what we are doing is a thin layer of polysilicon is grown over the entire chip surface. So after this what we are going to do is, after formation of this thin layer of SiO2, so what we are going to do is, gate formation means compulsory you require a polysilicon. Okay, polysilicon is nothing but it is heavily doped silicon material, so that is nothing but the polysilicon material. So here a thin layer of polysilicon is grown over the entire chip surface by chemical vapor deposition. So already we have seen this one, chemical vapor deposition. Okay, so here after forming SiO2, thin SiO2 on the surface, what we are going to do is we will place a polysilicon layer. Okay, so that polysilicon layer will be placed by using chemical vapor deposition. Okay, and photoresist is also grown over a polysilicon. So what we are going to do in this seventh step is, so after forming our thin SiO2 on the wafer surface, next what we will do is we will form a polysilicon by using CVD, that is chemical vapor deposition. On that polysilicon we are going to present, or we are going to cover with photoresist. That's what here I have clearly indicated, that this is nothing but the thick SiO2 what we have considered in the second step. After that we have formed thin SiO2, so that will forms like this, and next what we have done is polysilicon to form the gate. Okay, so and at the same time, whenever you are forming a region, means you have to use a photoresist and at the same time mask. For that purpose I am going to place the photoresist on the top of this polysilicon layer. So you can clearly get here thick SiO2, thin SiO2, and at the same time polysilicon we can represent with red color in our layout design. Okay, our color coding, that is schematic, what we call stick diagrams. Okay, stick diagrams and layouts, the polysilicon one color will be represented with the red, and it will be represented like that in the backslash in the layout design. Okay, so that's why I have represented here also the same thing, polysilicon. So here we have photoresist, this is totally photoresist, this one is the polysilicon. So this is the seventh step what we have to use. So after forming the polysilicon and photoresist, we have to use the mask. Okay, to form the gate, polysilicon gate, we have to use the mask. After using the mask, we will expose that one to the UV light. After exposing the UV light, what we will do is we will remove the polymerized and non-polymerized photoresist. That is the next step what we have. So that is, next one is the photoresist is exposed to the UV light by using the mask to pattern the polysilicon to form the gate. Okay, so where we are going to form, that will be patterned by using the mask. Okay, so that is what here we have, the photoresist is exposed to the UV light by using the mask to pattern the polysilicon to form the gate. Okay, after using the mask and after exposing the photoresist to the UV light, so next what we have to do, previously what we have done is nothing but we are removing the polymerized and non-polymerized photoresist, and at the same time whatever the non-required materials. Okay, similarly here also we will do the same thing, the polymerized photoresist and thin SiO2 and polysilicon will be removed. At the same time the unpolymerized photoresist etched away. Okay, so that is what here diagrammatically I have shown in these four diagrams. You can observe here what we are using the mask, and at the same time this photoresist is exposed to the UV light. Okay, so this photoresist is exposed to the UV light, and from this point to this point, from this point to this point, and at the same time from this point to this point, there is no light. From this point to this point there is no light will form, UV light, and at this point and at this point the UV light will falls. That means what, the photoresist present from this region to this region and this region to this region will be exposed to the UV light. Whenever it is exposed to the UV light, here we are using negative photoresist, so that will be hardened. So this, up to this material it will be hardened. Okay, so after that what we have here also that photoresist is exposed to the UV light, at this point also the material, photoresist material will be hardened, and there is no effect that will be takes place at this point. Okay, that's what we have drawn like this here. So after this applying the UV light and at the same time that one, so we will have here, one second, we'll have here, like suppose this one is what, polymerized photoresist, and at the same time this one is also polymerized photoresist. So we will remove the polymerized photoresist and at the same time here we have thin SiO2, that is nothing but here we have thin SiO2 is also there. Okay, so here also we have thin SiO2. So this polymerized material and thin SiO2 will be removed. At the same time under that polysilicon is also there. So if you observe this one, whenever the light falls on this one, this photoresist is hardened and this photoresist is hardened. Under that what we have? Polysilicon we have, and at the same time silicon we have. So we have to remove this polymerized photoresist and at the same time whatever the material, that is what, polysilicon and at the same time thin SiO2 under this photoresist, hardened photoresist. We have to remove all these three. Okay, and unexposed region of this photoresist is also we have to remove. That is the step we are having here. So first step is what, we are using the photoresist and that will be exposed to the UV light by using the mask. After that what we are doing is we are removing the polymerized hardened photoresist, and under that we have polysilicon and thin SiO2. All these three will be removed. If I remove all these three, so what you will get? You will get like this. If I remove all these three, you will get like this. Okay, so if I remove all these three, I will get like this. This one and this one and this one I have to remove, and at the same time here also this one and this one and this one I have to remove. Okay, that is photoresist, hardened photoresist, polysilicon, and at the same time thin SiO2 I have to remove. And this will be as it is, it will be present after removal of these things. Okay, so this one is from this point to, so this side it is removed and this side is also it is removed. The remaining part will be obtained here. Okay, so after this one up to this point, right, up to this point, what is the diagram that will obtain is nothing but this diagram. Okay, so after removal of hardened or hardened photoresist with polysilicon SiO2, that is thin SiO2. We don't remove any thick SiO2, thin SiO2 we will remove. Okay, so after removal of hardened photoresist with polysilicon and at the same time thin SiO2, we will get the diagram like this. So this diagram will be obtained as like this. But we are not removing at this point directly here the unexposed photoresist. Okay, that will also we can remove in the next step. So in the next step what we will do here, so at the same time unexposed, unpolymerized photoresist will be etched away. Okay, so this will be etched away. So this is nothing but unexposed photoresist, unexposed photoresist, and this will be removed. Unexposed photoresist, that will be removed, so that we will get the diagram like this. So this is nothing but the thick SiO2, and this one is the polysilicon gate, and at the same time we have thin SiO2. Okay, so it is metal oxide semiconductor FET. Okay, that is nMOS means. So therefore it is the oxide, thin oxide what we have, that will isolate the gate and at the same time the substrate or the silicon. That's why it is called as metal oxide semiconductor, nMOS. Okay, so here we have thin SiO2 under this polysilicon, that will be considered as the polysilicon gate for us. Okay, so this is thick SiO2, as it is it will be present. Now the gate is formed, gate is over. Now what are the remaining terminals we have? That is source and drain. Okay, in nMOS transistor we are taking the P substrate, and at the same time the source and drain will be of N diffusion or N type materials. Okay, so therefore after forming this one, so I will use the diffusion process, and I will use the diffusion process, and I will send the pentavalent atoms to here. Okay, so here what I am doing here, so after formation of this gate, now we have to form the source and drain. So for that purpose what I am doing, I am using the diffusion process. Okay, I am using the diffusion process, and I am placing the, or I am sending the pentavalent atoms like phosphorus, arsenic and antimony and bismuth to form the N plus source and N plus drain. So here if I send these pentavalent atoms by using the diffusion process, so the N plus and N plus will be formed. This will be considered as the source, and this will be considered as the drain. Okay, this is the gate. So this is how you can form source, gate and drain. In between source and drain we have the empty space, that is used as a, or that will be the channel region or channel area in enhancement transistor. Okay, we have not placed any channel, but the gap is there between source and drain, that will be considered as the enhancement transistor formation. Okay, and we have the final step, that is nothing but here one very important point is there. Okay, so this gate is protected, okay, from the diffusion process of this formation of source and drain by the SiO2 and at the same time the polysilicon. Okay, so that's why it can, here there is no using of mask, because the polysilicon and SiO2 will protect the surface from the dopants, from the diffusion process. Okay, from the diffusion process. That's why these are called as, this is called as self-alignment mask. Self-alignment mask. So here the polysilicon and SiO2 are protecting the surface from the dopants. So this is called as, here poly and SiO2 are protecting surface from diffusion. So this is called as what? This is called as self-alignment mask. Alignment mask. Okay, so there is no need of using the mask here, because the polysilicon and SiO2, thin SiO2 are protecting the surface of the wafer from the diffusion process. Okay, that's why it is called as what? Self-alignment mask. Okay, so it is self-alignment mask. Okay, so next what we have to do is we have to form a contact cuts, and at the same time the metal contacts, metallization we will do. That is the final step of fabrication of this nMOS transistor. So after the formation of source, drain and gate, now we have to form the contact skirts for the source, drain and gate, because we have to connect those source, drain and gate to the external by using the metallization process. Okay, so before doing the metallization we have to go with the formation of contact cut. For that purpose, a thick layer of SiO2 is grown on the surface, and on that one we will place again the photoresist, and that photoresist is exposed to the UV light. Okay, so that's what we are doing here. So after this one, formation of the source and drain, okay, so we will place SiO2, thick SiO2 again. On that one we have placing that photoresist. Okay, so after that I am using mask here by placing or by exposing this photoresist to the UV light. Okay, so here I am placing the mask. So at this point and at this point and at this point there is no light coming towards the photoresist, but in this place, from this point to this point, and from this point to this point, and from this point to this point, and from this point to this point, the light will falls. Okay, so wherever the light will falls, the UV light falls on the photoresist, that material will be hardened, and that is nothing but that we can remove that. Okay, so that hardened material can be removed, and at the same time we have to remove the unexposed photoresist. Under it we have what? SiO2 also. Okay, that SiO2 also we have to remove. That is the point. So what we are doing in the step 10, after formation of source, drain and gate, we have to form the contact cuts. For that purpose, again I am forming thick SiO2. On that one I am using photoresist and I am using the mask. Okay, to form the contact cuts. So how we can form the contact cuts means, so here this is what? Here polymerized. Okay, this material is polymerized because the light is falls on this one. Okay, and here also we have what? Here it is polymerized, and here also it is polymerized, here also it is polymerized. That is a hardened material. So we can remove that hardened material, and after that what we have here is the unexposed material, the unexposed area. So that unexposed photoresist and the whatever we have here, the SiO2 will be removed. Okay, that's what here in the step 11. So the unexposed, unpolymerized photoresist and SiO2 under it are etched away. So this one is the unpolymerized photoresist. Under it we have SiO2. These two will be removed first. So after that, whatever we have, the hardened material, that can be also removed. So here the unpolarized photoresist and SiO2 under it are etched away, so that we can form the contact cuts for the source, drain and gate. So those contact cuts are this one and this one and this one. Okay, so whatever we have here, this material, that is unexposed photoresist, under it we have unexposed photoresist, under it we have SiO2 layer. These two will be removed, so that there will be a formation of contact cut for source. Similarly it is for gate, similarly it is for the drain. So all the contact cuts are formed, and at the same time what we will do is we will strip away whatever the exposed photoresist or polymerized photoresist. Therefore you will get the final structure as like this. So this is the contact cut for the source, this is the contact cut for the gate, and this is the contact cut for the drain. Okay, so this is how these contact cuts will be formed. So after the formation of contact cut, so what we will do is, again we will place the metal of thickness. Okay, so metal of thickness, here it is 1 micrometer thickness. Okay, and again we will do the same process whatever we have done for this formation of contact cuts. So we'll repeat the same process, that is using of the photoresist and mask, and if you do that we will get the finally here we have the structure of nMOS transistor. So here the last step is, the final step is, now the metal is deposited over the surface of the chip of 1 micrometer thickness, and it is also placed photoresist and exposed to the UV light. And finally if you remove the unpolymerized, okay, or unexposed area or the photoresist if you remove, and you will get finally the structure of nMOS transistor in the fabrication. So finally the exposed photoresist, whatever the exposed photoresist we have, and metal if you remove, and at the same time unexposed photoresist if you etched away, so you will get the structure of our nMOS transistor in the fabrication. So you can observe here, this is the metal and this is the metal contact and this is the metal contact. What you will get after this metallization process, the same process will be removed, forming of the metal layer, and at the same time on that one, if you use the photoresist, again you can use the mask and you expose that photoresist to the UV light, and if you remove the unpolymerized and polymerized photoresist with the unrequired metal, so you will get this type of structure. Here this one is the source, drain, and at the same time here polysilicon gate and their contacts, cuts, and at the same time the connections to the external world. So this is about the fabrication of nMOS transistor. Okay, so this can be repeated, the same steps will be repeated for the PMOS fabrication also, but instead of taking here P substrate for PMOS transistor, we will consider the N substrate, and at the same time the source and drain will be formed by the P plus material. Okay, this is the only difference, and all the remaining steps are same as for the PMOS transistor fabrication. Okay, thank you for watching.